All right, elements of high-quality programs. We will learn about declaring and using variables and constants. I think I talked about this, did I not? How you denote a constant with capital letters, and then you give your variables names with lowercase letters. At least that's the convention. It's not like your program's not going to work if you do that. Performing arithmetic operations, the advantages of modularization, modularizing a program. That's kind of the stuff we're going to talk about. Now, what this textbook calls modules, we're going to call functions. And that's common programming lingo in a lot of programming languages. You write functions. And a module is something slightly different. A module is a collection of functions. But that's okay. If you see a question, on my exam, I'm never going to make you pick between the options of module versus function, right? I might put functions last module, just to remind you that I consider them both the same as far as the textbook. But I'm going to try not to confuse you when I'm changing the terminology about what I want things to be called. So the advantages of modularization. If you wrote a program that was 100 lines of code, just straight top to bottom, 100 lines of code, if you can break out parts of that code and put them, some languages call them subroutines, others call them functions, modules. If you can put chunks of code, give them different names, then you're much better off. Why? Because you can test each one individually, or you can give that code to somebody else to inspect. So for example, say that you have some code that opens a file, reads all that data into a memory structure, then processes that data to modify it, writes it back out to the file, closes the file. You could do that all in one straight shot, but you could also break it up. Function 1, open the file. Why would you want to modularize that? Because there are things that can go wrong when you try to open a file. The disk drive may not be there. The file name may be bad. The drive letter may be bad. All that kind of stuff. Y'all use computers. You have seen plenty of file errors. So that would be one. And if it was one module, if it was malfunctioning, you would know exactly where to go in your code to fix it. And then the next one, read file into memory structure. If it's in its own function, you know right where to go if you need to modify the way it reads from the file. What if instead of reading from a text file, it's going to access a database and pull it back in, right? Or maybe it's supposed to access something from the internet. You go and you change that in one place, and you don't have to scroll up and down your code looking for where it happens. If the code's already got a name, read data, you just go right there and you fix it. And yeah, that change may require you to change another module, but at least it's easy to spot those modules. And if you're working with another programmer or you're giving out assignments or, somebody can tell you, okay, the read data module is not working if blah, blah, blah. If they typed in too many spaces on this field or something like that. And then you go and you fix that module. You know exactly where it is. You're breaking it down, just like a car. If you take your car in to get it repaired, you don't want them to start examining your car from bumper to bumper to find out what's wrong. Instead, you want to be able to say, okay, my engine's rumbling, and then I go, okay, well, it sounds like a carburetor problem, or whatever. Nowadays, it's all computer problems. Well, we're going to have to pull out your, your module and put in another $700 computer part. Okay, great. I was hoping you'd just, tune something. Anyways, change a fuse. So breaking things up into modules is a really good thing. Another critical reason why you do that is what if once you've written an awesome program, you want to take it and change it and write a new program with it. Call of Duty 1. And then you're going to rewrite it and you're going to create Call of Duty 2 and make a whole bunch more money. Well, you can be sure that those programs are written very, very, very modularly. That's probably not a word. Modularized. So that people can go in, take parts of the code, bring it into their own code, and already have an up and running system that they can then modify. And people even do that, and then they sell their game engines, like the old game Unreal. The guys who programmed Unreal then turned it into the Unreal Engine, which they sold to other game makers. And those guys could use those modules to make their own games. So modularizing is a very, very good thing. And that's what we're going to work on today. A little bit of modularizing. So modules Our subunits, like I was describing, one part will be the engine, one part will be the steering system or whatever. One part will do one thing, one part will do another. They're called subroutines, procedures, functions, methods. They have a name, and then they have a block of code associated with that name. So that in your main program, you can call it by its name. You call it with one line of code, rather than the 10 or 100 lines of code that the module might have. So modularization is breaking down a large program into modules. One thing you do with modularization is to make sure you're not copying and pasting code. So like if you write code that asks a user for a number and then multiplies it by itself and then displays the result, but then you want it to be able to do that 10,000 times in a row, you don't want to copy that code and paste it 10,000 lines in a row in your program. That's extraordinarily bad. Instead, you'd make it a module and you'd make it loop calling that module until they wanted to quit. So anytime you find yourself copying and pasting into your program to repeat some code more than once, go, whoa, I maybe need to modularize it. Maybe twice is okay, but if you do it more than twice, if you put the same code in your program 3, 4, 5 times, not a good thing. You ought to make it loop and you ought to make it modularized. So abstraction. If something is modularized, you can consider it abstraction. Now, if you read a lot of fiction books, you'll see people use the word abstracted to mean distracted. I argue with that that's the correct use of the word abstraction, but they surely seem to use it a lot. In our case, what it means is you think about the problem in larger level than just the details. Abstract details, I don't know, they're not abstract really. You have to actually figure out how to do it. But you could think conceptually, okay, I'm going to draw a flow chart that says open file. The next block is going to be read file into memory. The third one's going to be process memory, making changes to data. The last one, second to last one, is going to be write data back to file, and then the last one under that is close file. There, you've already figured out what it needs to do. That's the abstract level. That's the high level. Then you go in and you start writing modules in order to solve that task. You go in and you write some code that opens the file. Don't even have to do anything else. You write that one module, you test it and go, yeah, cool, I've got some code that opens the file. Then you write your second module, the one that's supposed to read the file in and put it into data. You write that code, you test it out. You don't want to write 50 or 100 lines of code, then try to run it and have to fix 17 errors, right? Now, when I'm walking around helping people, sometimes you have 17 errors because I can't stop every 2 minutes to help people. But really, you want to run your code as often as possible. And with larger and larger projects, you can't really run it, every 5 minutes. But you can write a module and then test it. You can write a module and then test it. Selective ignorance. I don't have to know how the file is opened. If I'm working on a team, I can just, ask somebody to write the code that opens the file or reads it into memory. Or I write it once and then I kind of forget how I did it. And believe me, if you become a professional programmer, you're going to learn a lot of stuff that you will then kind of do that. You'll just file that knowledge away and you go, okay, I know that I know how to do it, but I don't have to keep it stored in memory, in your brain, because I can always go and look it back up, right? Half of programming is just learning about the concepts and being confident that you can know and figure out the details the next time you need to do it again. So one broad statement corresponds to a dozen of instructions. Open file, read file, process data, close file, kind of like the big blocks on a flow chart. Each block on a flow chart may need to run 15, 20, 100 statements in order to work. Let's give some examples of that now that I've talked for 24 minutes. We're going to use something called turtle graphics. Now I'm going to bring up a page about turtle graphics, and why don't I post a link to it right now? We have an online textbook posted, I hope. If not, I'm going to post a link to it right now. So go ahead and open Python. We're going to use it. All right, I'm not seeing our online textbooks folder. So I'm going to make one. All right, this is drawn from a textbook called How to Think Like a Computer Scientist. And I'm going to be bopping over here because it's Python specific, right? The book covers a lot of things. It covers Java and C++ and stuff like that. But we're also learning Python specifically, not just, So this is a really good textbook. All right. Pretend I know how to spell correctly. All right. All right, there's a folder under Contents now called Online Textbook. I'll drag it up so it's near the top underneath Class Information. I'll also post a link to it right on the front page of D2L, make it really easy to find. And then we're going to go to the chapter called Hello, Little Turtles. You'll see as we do this, this looks considerably different than the, the scholarly textbook that we're reading. Okay, so I want the chapter called Hello, Little Turtles. I'm just going to kind of use it as a reference. I'm going to flip back to it, to remind myself so if I get stuck on something. Like I said, you don't have to learn everything. You just have to learn that something is possible and then know that you have resources to show you how to do it. Okay, so I'm going to make a new file, save as, save it in my favorite work directory. February 15.py. Name, date, explanation of program, turtle program to illustrate functions, modules. At some point I'm going to start counting off if y'all turn in homework that doesn't, have good comments in it. There's absolutely no reason why you can't take the time to type in 2 lines, a couple of lines at the top. Alright, so the first thing we need to do is do this line, import turtle. Turtle has to be all lowercase. What that means is that somewhere in the Python installation, there's a library called turtle, probably in a file called turtle.py. This brings in all the functions of the turtle library, all the modules, so to speak. Now we need to create a turtle, and we need to create a window for the turtle to draw on. Fortunately, that's just 2 lines of code. Modules. Modules are good. So the first one's going to say when is equal to turtle, all lowercase, dot, make sure I get it absolutely right, turtle dot screen with a capital S, parentheses and parentheses. All function calls have to have parentheses at the end. And when I'm walking around and helping you, a third of the errors are going to be because people left off the parentheses. You'll get used to it. Okay, so that's going to be our window that we draw on. Maybe let's change the background color. Win.bg color, I don't know, silver. Then at the bottom, I'm going to do this, win.main loop. What that means is the library is just going to sit there looping until you close the turtle window. That's kind of like adding the input statement at the bottom of the program that I've kind of told y'all that you can do if you want to be able to run the program by double-clicking it from within Windows. I'm just going to run it to make sure all that stuff works. All right, it drew my, my gray window. I'm going to close it. Now there's a page we can go to get colors, all the possible colors that this library supports. I feel like posting that in D2L too, just because colors are awesome and you may want to pick your own. So what you do is if you're not at D2L, you type in TK color Python 3, something like that. Or even just TK color would do it. TK color meaning toolkit color. Maybe that was the bad choice. TK colors Python. Well, that's hard to read, but that would probably work. Okay, if you click on it, it becomes a little easier to read. Okay, that looks like a good one. I'm going to post a link to this in D2L. Stop it. So that you can find the color chart. Turtle colors. Come on. I want the URL itself. Yeah, there it is. All right. All right. If you go back to D2L, you can find a link to the color chart. And you don't have to use it, but it's nice. Nice to be able to pick. And you'll see that there's hundreds and hundreds of colors. Cyan, cyan 2. Goldenrod, khaki, dark olive. Okay, great. So I just chose silver because it came to my head. Now we're going to create a turtle. Make a turtle draw. Okay. So I'm going to call my turtle Leo, like Leonardo the Ninja Turtle. So Leo is equal to turtle dot capital T, turtle, parentheses in parentheses. And do you need these spaces between the parentheses? No, but I think it makes it easier to read when you're looking at the screen. Now I'm going to make the turtle move. I could type leo.forward, but I can also type the abbreviation because I've learned that people type forward or, you know, without the R. Okay, so leo.fd, and I want him to go 100 pixels. And I don't need that dot there. That was my mistake. Leo.fd, go forward 100 pixels. Forward 100 pixels. And then I'm going to make him draw a circle. Leo.circle 100 pixels. Then I'm going to make him turn left. Leo.left 90 degrees. You know, 90, 180, 270, that kind of stuff. And let's make him go forward one more time. Leo.fd, and then I'm going to walk around and make sure that y'all are all good. Alrighty, so he went forward, you know, 100 pixels. He drew a circle, he turned left, and he went forward another 100 pixels. What if we wanted to see him do that in slow-mo? We can do that. I said I was going to walk around, but right under where I create the turtle, I'm going to change his speed. So right underneath that turtle.turtle line, I'm going to add leo.speed 1. That's going to make him go as slow as possible. 1 is the slowest speed, just like 1 mile per hour. All right, now he's drawing really slowly. That's really fun to watch, and then after a couple of times, you get really tired of him going that slowly. If you get tired of him going that slowly, you can comment that line out, or you can change it to 10, which is almost the max speed. 0 is actually the max speed for some reason. Okay, it's going faster. That's nice. If I change it to 0, that's the max speed possible. It'll be just about instantaneous. Boom. All right, that's a bit much. I don't want it to go like that, so I'm going to change it back to 10. But I'm going to make a comment. 1 to 10, or 0 for fastest. It's not a bad thing that that happens. It's just something we have to fix on our own time. Okay, so, whoops. We have our program here. Let's make it draw a rectangle. How do you draw a rectangle? You go forward a certain degrees, you turn left or right 90 degrees, you go forward again. How many sides does a rectangle have? A square has? It has, 4 sides, so we're going to need 4 commands. We're going to have to turn left or right 90 degrees 4 times. So I'm going to delete some of this code here. Alrighty. So right now I only have 1 line of commands other than the speed. And by the way, if you want to change the color of your turtle, you can do that. Let me show you how first. Above that forward, I'm just going to add a color command. Leo.color, it's going to be red. So Leo.color, parentheses, quote, red. That'll change the turtle to red. Alrighty, so we want him to go forward and we want him to turn left or right 90 degrees. I guess we already had that, but alrighty. Not 100 degrees, that's not a square. 90 degrees. Now he's got to do that 3 more times, right? So I am going to copy and paste just after I said not to. So I'm going to copy those 2 lines and I'm going to paste them 3 more times so that he draws a total of 4 lines. But in the back of my mind, I'm thinking I shouldn't have had to do that. I ought to find a different way of doing that. Okay. So that's, like side 1 we just did. I can add some comments. The first forward 100 is side 1. The next forward is side 2. The third forward is side 3. And the last forward is side 4. All well and good. Let's test them out. Alright, he's still going lickety-split. I might slow him down, but you see, it drew a square. That's all good. Alrighty. But what if we wanted to be able to draw a square with just 1 command rather than 8 commands? We don't want that. We don't want to have to type 8 commands every single time we draw a square. We're going to want to put that in a function. So I'm going to demonstrate that and then I'll do another walkabout. What I need to do is I'm going to indent all of these turtle commands from there down to there, 1 level. So I'm going to highlight them all with my mouse or my cursor keys. I could do format, indent, or I could hit tab, like that. But I have to give this block of code a name. I have to call it square so that it can be repeated over and over. So the way I give a function a name is I do this line right above the turtle commands. DEF space square, parentheses, in parentheses, colon. That defines a function called square. Now the rules for a function is they have to be defined exactly like that. DEF, give it a name, then the parentheses, then a colon, and then everything in the function has to be indented. You don't got that, it's not going to work. Alright. Hey, I'm going to test my module out. And by the way, this isn't going to work. This is to show you something. Alrighty. He's not drawing a square anymore. That's because When you define a function, it's like writing a page in a cookbook. The cookbook doesn't actually make your cake. But you can tell somebody, you know, go to page 39 and make the cake for me. We have to tell it to draw the square. We have to call the function. So near the bottom above our main loop, do this, square, parentheses, end parentheses, like that. And we're back in business. So why is that so great? Because we could call the square function multiple times if we wanted to. Try this, gang, while I'm wandering around. Make the turtle go to the left or to the right, leo.left, a certain number of degrees, and then call square again. And then keep doing that. Just repeat those two statements a couple of times. Run it every time you make a change. So now if I do that where it is, boom, it drew two squares, right? So that's pretty cool. You know, we got it to execute 8 lines of code just with a single word. So we've modularized our code so we can draw a square anytime we want with a single command. So just play with that. Make it turn left another 20 or, you know, 40 or 80 or whatever. Then just doing this. This is annoying, right? If for every square I draw, making it turn left, right, like that. I don't want to make it do that. I want to make it loop. Looping is incredibly important to computers. Looping is pretty much what computers are all about, so that they can repeat a task hundreds of thousands of times or whatever. So what I'm going to do is I'm going to make what's known as a while loop. A while loop repeats. Seems like we did a while loop already. Well, we're going to do another one. I'm going to make a loop, a variable called I, just for fun. You're not supposed to use single letter variable names, but for loops, I don't really mind. So I equals 1. And by the way, I've got these lines of code kind of left down here. I'm going to wind up tabbing them over. Yes, sir?
I'm sorry, I can't really tell, but are you putting a space after your I?
Yeah, but that's just for reading. You don't have to do that.
Oh, you don't have to?
Right, right, exactly. My spacing is to try to make my code easy to read. I don't care if you do it. There's very few times where spaces count. The most important one is the tabbing. Code doesn't work if you don't have that tabbed right. Like so if that's only 3 spaces and that's 4 and I do a run, kablooey.
But if they were all even in one tab, would it still...
Exactly, it would run.
Oh, okay.
And I did not mean to close my code. Very good question. Alrighty, here we go. Alright, let me fix that. Okay, so this is my loop variable. It's going to count. So while I is less than, how many sides do I want to draw? I don't know, 8. But I need to make it less than or equal to 8, right? Because it's going to go 1, 2, 3, 4, 5, 6, 7, 8. If I just made it repeat and while it's less than 8, it would only actually get to 7. So there we go. While I less than or equal to 8, colon. Why the colon? Because every time I start indenting, I have to have a colon on the line above it. So let's draw a square. And again, the space here is just for make it easy for y'all to read. And then let's turn them left. I'm going to type in a value, but then I'm going to want y'all to actually figure out the correct value to make it draw, you know, like a complete circle full of squares. I know somebody will be able to figure it out. And then we better increase I, because if we don't increase I is always going to be less than 1. It'll be an infinite loop. Hey, let's demonstrate that. I'm going to change the speed of the turtle back down to a reasonable value, though, so that we can watch that go. All right, so this is broken code. This is not good code. All righty. Hey, I like it. This is pretty awesome. All righty. Yo, can we stop now? Hey, stop. Okay, so yeah, the problem with that is that we never changed I. So this condition is always true, so it never stops. So I'm going to do this. I equals I plus 1. Then I'm going to run it again. Oh, and I don't need this final square line, or this final Leo dot left. I need to get rid of everything down to, but not including the main loop, right? So this is my only actual drawing code anymore. The rest of it, I've kind of replaced. Don't want it there. Alrighty. But if I wanted it to complete the circuit, I would either have to change the maximum number of sides, or I would have to change the angle. How many squares would I need to draw in order to get it to look perfect? If you can't figure it out, that's fine, but if somebody blurts out the answer, that'd be awesome. 12? All right. 12 is correct. How do I know that? A circle has 360 degrees. And if you divide 360 by 30, you get 12. So if this angle was like 90, 360 divided by 90 would be 4. All right, I'm going to speed them up a little more. Okay. All righty, I'm digging it. Let's make another function called triangle. This will be close to the last thing we do today. How do you make a triangle? What angles do you go to draw a triangle? Well, it's got 3 sides, right? So what are the angles going to be?
It depends on what type of triangle you want.
That's true. I want it to be a perfect triangle, though. Whatever this is really called.
33, 33.
Well, it'd be 360 divided by 3 because it's got 3 sides, so that's 120. So let's define a triangle function. DEF space triangle parentheses in parentheses colon. He only has to draw 3 lines. Leo dot forward 100. Leo dot right 120 degrees. And again, we ought to put this stuff in a loop. But it doesn't take that long to copy and paste that stuff to make it draw 3 sides. For now. I'm just doing that for speed. Bad programming, but that's okay. And so that first forward is side 1. That second forward is side 2. And that third forward is side 3. Now go and change your code down here to draw a triangle rather than a square. Just comment out that square line or something. And make it a call to triangle instead. So I just commented that line out. That's why I'm marking it with those things. You don't have to put those things out there. And I just added that line. Again, you don't have to put those red marks out there, those comments. All right, that's kind of slick. I'm digging that. What if I want to make it a triforce? It's only going to have 3 sides. So I need to change that to I is less than or equal to 3 because I only want it to count up to 3, right? Now I'm about to do walkabout again, so if anybody's stuck, no problem. All right, well, if I'm going to draw 3 triangles, what do I need to change that 30 to? Just like we figured out up here, 360 divided by 3 is 120. We might think to ourselves that we could calculate that angle based on that angle, and we can make our code more flexible by defining variables that would hold that stuff. But All right, that's cool. That's kind of right. That's kind of wrong. I think I'm going to make him turn to the left rather than the right. See if I like the way that looks better. So up here where it says right, right, right in the triangle function, if you care, you don't have to, make those angles left, left, left up in the triangle function rather than right, right, right. Now see, if I made it a loop, I'd only have to change it once rather than 3 times. So because I was lazy at the beginning, it's requiring more work at the beginning, at the end. Okay, that's still not right, but I'm gonna live with it. All right, I want to make sure that a lot of y'all have triangles on. Last thing I want to do. Oh, by the way, all the mistakes that I helped with were just things like typos. You know, if you spelled it triangle, not gonna work. If you missed the colon, not gonna work. Okay, so the way you fill in this language is you issue, well, for this library, a begin fill command up at the top and an end fill at the bottom. So for the triangle function, we're going to insert a line here. Don't type that, I'm just showing you. And there. We need to begin our fill here. We need to end our fill here. So we're going to give the turtle some more stuff to do. Leo.begin underscore fill. And then guess what the next one is at the bottom? Leo.endfill. And now that's pretty snazzy. Can you fill it with a different color than the lines that you drew? And the answer is yes. You see this line up here, the color? You can specify both the line color and the fill color. So if I want the lines to be drawn in red, but I want the fills to be done in yellow, I would change this color line to add the second color, which is the fill. So it would be red, quote, comma, and make sure this stuff's still inside the parentheses. Red, end quote, comma, beginning quote, yellow, end quote, like that. Anybody else have any suggestions? I have one in mind. See if you have telepathy. For what might be cool to do. Not change the shape of it, but another thing that'll make it look interesting. Yeah, I could change the background. When you got a paint program and you're drawing with a paintbrush, what can you change about the paintbrush besides its color?
Size.
Yeah, the size. Let's see if we can change the size of it. I'm cheating. I'm going to, the command is called pin size. And here's an inconsistency. Pin size is not going to have an underscore in it, but begin and end fill did. Probably 2 different programmers wrote those 2 functions and they didn't care about making their function names consistent. So up here where we define the speed of our turtle and the color of it, let's add one more command to make it a little thicker. So underneath Leo.color, I'm going to do Leo.pinsize. Parentheses in parentheses. Then I'm going to run them. Well, I can't say that that did a darn thing. What did I do wrong? I forgot to put a value in here, right? I forgot to say that, I want my pin to be 5 pixels wide. So that's my new line of code. I forgot the 5, my mistake. Sometimes I make mistakes purposely to demonstrate to you all. Half the time I don't. I should claim that they're all intentional though, right? Okay, so there we go. The very last little thing I think I might want to do is to hide the turtle so that I don't have that cursor there at the end. Because it's fun to watch the cursor draw it right, but you might not want it at the end of your drawing. So I think it's just .hide. So after I change its pin size and its color and everything, we're going to make one more change to our turtle. Let's see if I got it right. Hide. Parentheses in parentheses. No, that's not right. Okay. See there? Professor is happy to admit he doesn't know everything because you can't learn everything about programming. What do I mean by that? It's just too large of a field. Alrighty. Hide turtle, not hide. And again, there's no underscore. So I need to change that line one more time to make it hide turtle. Then I need to take roll and make a drop box and stuff like that. Make sure y'all have a homework assignment. Alright, the turtle's gone. I'm happy with it. Do I need to walk around? I'm not seeing anybody raise their hand. Alrighty, at the end of the class I'll bring this back up so that if you didn't get it working, or I can print it out for you. Because I bet I typed too fast for a couple of folks. Alright, I see people pointing at each other's screen. That means I should have done a walk back. You've done it right, we just have to do an end fill at the bottom. So underneath, yeah, so underneath that last dot left, do your dot. Right, you got the other score. Good deal. Hey, if we flickered the colors real fast, we could probably, you know, give somebody a seizure like that episode of Pokemon. Yeah. Way back when. Alrighty. So, I want some homework that does this. We're going to write a program, actually just a flow chart or whatever, that calculates something known as the BMI, body mass index. Now, the body mass index is not really an indicator of a person's health because a football player will have an extremely high body mass index just because they have a lot of muscle. But in general, they use it statistically to say, okay, you know, the people in America have a body mass index on the average of 27, and the ones in India have a body mass index of 19, and we can compare, you know, heart disease rates or whatever. So, the formula for calculating body mass is, well, golly, let's see if I remember. It's the height, no, it's the weight in pounds divided by inches, again, and you math majors say, okay, I should have just squared it, it would have done the same thing, times 703. I think I am going to rewrite that. That's kind of dumb looking. So I'm going to make, and you don't have to type all these in. These are going to be part of the assignment. 703 divided by inches to the power of 2. That's the formula. So the task is to calculate a BMI, which is also known as the body mass index. Okay, so if we look at it, we're calculating BMI, but there are two values we have to have. What are those two values? Right, there's two more variables up there besides BMI. If you were going to write a program to do this, what would they have to be? Yeah, we need the pounds and the inches. So our program should ask the user for pounds. It should ask the user for inches. And then when it's all done with everything, it's supposed to display the BMI. The calculated BMI. Now I'm trying to make this not look too much like the pseudocode because otherwise you just change 2 words and you'd be done. Okay. That's what the homework is going to be. Homework, draw a flowchart or write pseudocode which is faster, right? All right, and I'll give y'all a sneak preview after this assignment. The next assignment is going to be to actually code it in Python. So if you feel like coding it in Python immediately, you know, because you're kind of bored, you don't have anything else to do all weekend, then feel free to do that because you know it's coming up. Alrighty, we need to take a roll and make a Dropbox.